I'm very pleased to welcome you today, Dr. Yuki Funabiki, and his talk is going to be about adversarial attacks in tabular data.
Today, I will describe the adversarial attacks for tabular data and the application to fraud detection and imbalanced data. And my name is Yuki Funabiki and from Sony Group Corporation. And okay, so let's go there, my description. And my first question is, what are AI incidents? We are now very interested in the AI incident because it affects the very business use case for of the corporation. And you can see the AI incident database. This database is organized by the partnership on AI. It is the how to say AI community. And if you visit this website, you can see every AI incident in real use case. And as AI technology is very integrated to the real system, for example, automotive driving and other ChatGPT, the large language model and other tasks. And the AI incident database is some tool designed to help researchers or other people to better imagine and anticipate these risks. And in the past, the AI incident database has over 1,000 reports, but recently they reformat their own database because they want to focusing on the real incident. It means how to say some corporation or some user the all some stakeholders affected by the AI model or AI system. And for now, there are 500 reports of intelligent systems causing safety, fairness, or other problems. And at first, I will share some information from this database. First topic is the harm type, and the incidents that are particularly harmful to human rights tend to be reported. For example, harm to social political systems or harm to civil liberties. And of course, there's a financial harm or other harm to physical property and other thing can be affected. So in that case, many researchers or many academic papers focus on some bias or transparency or fairness. But on the other hand, the harm time contains the financial harm or safety harm or other physical harm in this context. So in government or in corporation, they have to use their best effort to protect their stakeholder from these harm time. And the second topic is non-AI goal. So, the AI system or AI tool is widespread in all use cases. And this is the one example. And you can find the very famous machine learning task, autonomous driving and hate speech detection or other the chatbot. So these these tasks, their AI incidents has been already found. So in the future, we should we have to prepare with these AI threat. Uh, so our activity or this how to say the TrustML, trustworthy machine learning or trustworthy AI activities could be contribute to these preparation. And the final topic is non-AI technical failure. So this is the cause of the incident. So incidents can be categorized primarily as machine learning failures. It means how to say the non-malicious failure. So I mean, so sometimes the machine learning could be failed by overfitting or underfitting. In like that, so machine learning has such failure factor potentially. On the other hand, we should consider that there are some malicious attacker in the real field. So, for example, in this case, the adversarial data and the lack of adversarial robustness is linked to such malicious attackers. So you can imagine that adversarial data means attacker can prepare malicious data to teaching data, and other things. The lack of adversarial robustness means there are several AI-specific vulnerabilities or AI-specific threats, and attacker use such AI threat and AI vulnerability, and the machine learning model will be threatened by these attacks. So then I will describe the AI security or adversarial machine learning. So in this description, I will call the robustness to AI-specific attacks as AI security, and perhaps someone more familiar with adversarial machine learning. This is the topic name for AI security or other AI vulnerability. And in the academic area, many relevant papers have been submitted since 2014, and you know there are a very famous researcher, Nicholas Carorini, and he managed the number of papers related to adversarial examples or adversarial machine learning. And for now, there are over 6,000 papers, and this is very hot topic area in the AI or machine learning field. And in addition, this is the academic area, but of course, the many companies or many governments is focusing on this area. For example, the NIST, NIST, and this is the Americans organization, and they released the AI risk management framework in this January. On the other, of course, there are several company or organization has been released AI security guideline or AI privacy guideline, and I believe that this topic is keeping hot topic in the 5 or 10 years. And after that, the quick review of AI security. So I want to describe what types attack scenario in the this AI security area. And the last month, the OWASP released AI security and privacy guide. And this is very helpful resources for researchers, and I will describe it. And the OWASP is the open security community, and they have been released very useful security guideline or security tool. And for now, so they released the AI security and privacy. And this is the pipeline of AI or machine learning model. And at first, we should two factors. The first is regular application security. Of course, the AI or machine learning is software, so we should apply the classical security guideline to this material. On the other hand, there are other AI-specific threat, so we should additional such classical security, we should create a new new best practice for AI security and apply it our model or our system. And in the specific AI thread, they are separated two parts. The first is training phase, and the second is inferencing phase. In the training phase, the attacker can extract training data, or they can also contaminate the training data. On the other hand, we should consider about the supply chain problem. On the other hand, after the model building, so you can imagine after deployment the model, the developer or organization should pay attention the inferencing attack. In this case, attacker can be attacker try to submit their malicious query, and they try to occur the several malicious behavior of the model. For example, the model inversion or input manipulate attack, and the model shift or input manipulation black box attack. So like that, attacker can get the response of the model, because this is public. So attacker can get the response of the model, and they manipulate their input, and they can get a new response. Such iteration, attacker can fool the model, or attacker can handle the behavior of the model. This is a quick review of AI security, and today's my topic is focused on input manipulation attack. Attacker can manipulate their input query, and the purpose of the attacker is fool the model. And this is a quick description about input manipulation attack. And there are two settings, the black box setting and white box setting. The purpose of the attacker is the fool the model with deceptive inputs known as adversary examples, or the evasion attack. And they are classified according to whether the attacker has accessed the model or not. So in the black box setting, attacker can get the output label or output confidentiality. So in that case, attacker can manipulate, for example, you can imagine that attacker can manipulate the image, some red color in this example. And after, for the model, there are different inputs, but for humans, for human eyes, they are same context. But for the model, there are several input data, and the output perhaps different level. So this is the input manipulation and the effect result of the adversarial examples. And the other case, the white box setting. In that case, attacker can access the model. So the result of black box and white box is the same, but the attack capability is different. In the black box setting, attacker can access the only output from the model. On the other hand, the white box, attacker can access the internal parameter of the neural network or other machine learning models. So in the real use case, we should assume that the attacker is black box setting. But on the other hand, if we developer side, we can impersonate the attacker. So how to say that? Like offensive security, we can test our model as a white box hacker, and we can apply the more strong defensive approach to our model, and it means attacker, the model will be very robust for against the such attack. So this is how to say categorization of input manipulation attack, and in this topic we focus on the black box setting, and And this is our previous related paper. So the imperceptible adversarial attacks on tabular data. So it published in 2019, and this paper inspired us. And the key point of this paper is focused on tabular data rather than images. So for now, the adversarial examples is covered image, audio, and graph, and other data format. But in the 2019, the researchers uh, were focused on the image domain. But this paper is that this paper's targeted the tabular domain, and this is very interesting because many business use case in machine learning applications, they can usually use CSV format, the tabular data format, and they have shown that it is possible to attack even in a tabular context. So we should prepare such tabular data adversary examples in our business use case. And after that, this is the overview of our research. Adversarial attacks for tabular data, application to fraud detection and imbalanced data. And our motivation is here. We want to analyze AI risks used in business situation in advance. And we select the anomaly detection. The fraud detection model is assumed as a use case. And assume the attacker is an online user, so they can submit their malicious query, and they can get the response of the model, but they cannot access the model because they are online. And in this research, we developed some techniques to apply latest adversary examples attacks to tabular domain. And so I will describe the assumed use case. At first, this is how to say normal business use case. So there are one normal order. This is you can imagine that e-commerce situation, and some people submit their order via e-commerce online shopping, and the fraudulent model detect the order is fraud or not, the benign or not. So you can imagine that the normal order contains the value of transaction, the total of some counts, and credit card number, and some email domain or user agent. So in that case, we can imagine that normal attacker, so they use a long credit card. So the value of transaction is some different, and credit card number, they use a long credit card number, and sometimes they can change their email domain or user agent OS. But in ideal story, the normal attacker can change, can tamper their input, but the fraud detection model can detect such fraud order. So in that case, the normal order predicted as benign, and the normal attack order will be predicted as fraud. This is the first use case, or first business use case. And on the other hand, we should assume the attack scenario. In that case, attacker can attacker have some skill, and we assume the capable attacker they can modify the value of transaction and credit card number and email domain and user agent OS. For example, in that case, the normal order or normal attacker use computer, but the capable attacker use some smartphone. On that case, as a result, if the model if the attacker order fools the model, it means the attacker transaction will be predicted as benign. It means it's some harm to the e-commerce online shopping by their money. Of course, so this is the first scenario, and we in the real business use case, there are some operator to monitor some transactions. Of course, it is very hard to check all transaction, but with using machine learning model, they can pick up the suspicious input, and the human can check the only such suspicious inputs, and perhaps they can find the input is malicious. It means there are some wrong behavior of the model. So this is our but capable attacker can try to deceive the model and human eye. This is our attack scenario. And three issues addressed in our research. So in our use case, we use tabular data, and using some adversarial examples generation algorithm, but such algorithm cannot apply to tabular data immediately. And on the other hand, there are several issues, and I list up three items. So the first is how to apply attacks to binary classification using imbalanced data. And the second is how to consider the characteristics of tabular data. And the third is how to define imperceptibility in fraud detection. And I will describe each by each. The first topic is how to apply to binary classification using imbalanced data. In imaging recognition tasks, most of them are multi-class classification. So you can imagine that ImageNet or CIFAR has 10 or 100 class. So some existing generative algorithm has been also specialized to such multi-class classification. On the other hand, in the fraud detection, so you can imagine that the binary classification is more common rather than image recognition. And furthermore, data is sometimes often imbalanced. So the 10 or 100 classifications, the distribution of each class is very similar, but such fraud detection, so for example, the benign input is a lot of many and many, but the fraudulent input is very small, tiny. So such data imbalance can be affect the adversary examples. On the other hand, additionally, sometimes the gradient boost decision tree is preferred over deep neural networks. So in the adversary examples, many researchers select deep neural network or convolutional neural network, sometimes the graph neural network, but you can imagine that the real use case, you can access the Kaggle. This is a machine learning competition. Some competitor has been used gradient-based decision tree like XGBoost, RightGBM, or CatBoost. So we are interested in such machine learning architecture, except deep neural network and other settings. So as a result, the generation algorithm can be applied to the XGBoost model, and by setting an explicit target value as a threshold during adversary examples generation. And this is the first issue in our research. And the second is how to consider the characteristic of tabular data. And you can imagine that in the image data, each pixel value is defined as from 0 to 155 as RGB, or CYMK to from 0 to 100, etc. So some adversarial perturbations in the adversarial examples can be formatted these range. On the other hand, in tabular data, they could have many type of data. Discrete values, continuous values, and strings, Boolean values, or missing values. So it means if we create adversarial examples, perhaps it's very easy to detect because the number or the perturbation is very unfamiliar in the other data in the same column. So after generating adversarial examples, we should we format the data by ordering these limitations. So in additionally, so the minimum size of the perturbation must be carefully considered so that the perturbation is not cancelled. So it means if the data is, for example, the data is 1, 2, 3, 4, 5, and if the perturbation is 0 0.5, 0 0.1, or 0 0.2, so it means the adversarial examples produce the number as 1.1. But the original data column is int type, so it means if the after formatting, the perturbation could be cancelled or removed. So I think we apply some limitations for our generated adversarial examples. This is the second topic. And the last topic, how to define imperceptibility in fraud detection. So this is how to say a little bit ambiguous topic because imperceptibility is very difficult factor. For example, but in image you can imagine easily because if the perturbation is very small and it it located all pixels, it's very difficult to detect the perturbation exists or not. On the other hand, if the tabular data, so our question is the such imperceptibility could be ensured in the tabular data domain. So the result is it's a little bit difficult, but we define some metric, the custom metric. The metric were created to minimize tampering with the column of data, and that could be monitored by operators. For example, operator checks the total of some of their cost or other age or other factors, and if the such sensitive column could be tampered, the operator, we assume that operator can notice the tampering. And we have defined such metric in based on such assumption. So this is the last topic, and the experimental setup. This is the how to say the description of our experiment. At first, we selected the German credit data as a target dataset. This is a tabular format, and the dataset used to train a model to calculate credit risk in loan applications. They contain 20 columns, for example, the checking account status, credit history, and some age. And the records of this dataset is 1,000, and the ratio of the benign or fraud is the 700 benign transaction and 300 malicious transaction. We select also XGBoost algorithm, and we split the train and test data 7 and 3 70% and 30%, and running with 80% of train data. And the rest of other 20% was used as tuning threshold to improve the recall. For example, this is a quick sample of the model building, and we use XGBoost algorithm and scikit-learn algorithm, and we apply grid search hyperparameter tuning to model and use some. We also tune some threshold, because it means if the threshold is 0.5, it is default setting. Some accuracy is 95% or recall is 33%. But if in the fraud detection task, the recall is very important metric, because if the recall is low, it means there are several they miss their malicious input in the detection phase. So if the threshold is lower than 1.5, it means it releases some increasing false positive, but the recall could be ensured. In that case, so in this case, we tune the threshold. And after that, we use 3 type of adversary examples generation algorithm called as ZOO, zeroth order optimization, and boundary attack, and hop skip jump attack. This algorithm is black box adversary examples generation algorithm, and we calculate the success rate, success attacks for each algorithms. We execute our experiment step by step, and there are all 5 steps. At first, we apply these 3 algorithms to with default setting, but it's very difficult to find successful adversary examples. And after that, we tune the threshold in the generating phase and select more suitable initial perturbation. And after that, we can achieve the 100 success rate after that. And in the third phase, this is the first and second experiment. And in the third phase, we format our adversary examples, because in the second experiment, we find that very how to say, rough adversary examples. It means the operator can find the adversary examples easily. So we should more natural adversary examples. We try to create more natural adversary examples. So in that purpose, for that purpose, we format the adversary examples into our string or other float type. After that, the values number of values inconsistent with types will be 0 in the third experiment. So it means a little bit we can decrease the opportunity to detect adversary examples by operators. And in the fourth phase, we apply the which column is sensitive or which column could be monitored by operators. At first, we assume that operator checks 10 out of 20 features, and we select 10 features from the contribution to the classifier. In the XGBoost model, we can check feature importance to, it means which column could be contribute to the output. So such feature we ranked feature importance for each column and select 10 column could be monitored by operators. So it means in the fourth experiment, the adversarial perturbation should be applied to lower ranked columns. So because, for example, the purpose or credit history, if there are some perturbation in these columns, the operator could be could find the adversarial examples. On the other hand, the number of existing credit at this bank, so it is less interested by operators. So we try to more big adversarial perturbations to such lower ranked columns. This is the meaning of fourth experiment. In the last phase, assume attacker cannot modify 4 out of 20 features. So it means, so we assume that the attacker cannot modify the specific column, specific data. For example, they cannot modify the long credit number, or they cannot modify the total of cost. So sometimes this limitation fails the adversarial examples. So, but at least we find several attack success case in the final experiments. So this is the all description for our experiment. And this is my conclusion. So there are 3 challenges in applying adversarial examples to realistic business situations. But our research has shown that these challenges could be resolved. So AI security must be considered from a real-world operational perspective, and as any challenges could, in fact, be solved by attackers. So this is my conclusion, and thank you for your attention. Do you have any questions?
So you have a question, what are the differences between the algorithms or methods in slide 18?
Okay, so there are a little bit difference among 3 algorithms. At first, the zoo algorithm is okay, so they are split 2 types: the zoo and boundary and hop skip jump. The zoo algorithm have to use output confidentiality. For example, in the response of the model contains the output label. So this is benign or this is fraud. And the algorithm have to use other information like confidentiality. So it means this transaction is 19% benign or 10% malicious. So the zeroth order optimization use such confidentiality to their optimization. And the second, the boundary and hop skip jump is label-based black box attack. It means they don't have to use such confidentiality information. They only use output label, the malicious or benign. So this is the difference between the big difference between among them, and the difference between the boundary and hop skip jump is how to say, they use the same concept, but hop skip jump is more efficient than boundary attack. So you can imagine that hop skip jump is improved boundary attack. I think it's correct.
We have a question from Thibaut, maybe, if you can.
Yes. Yes, I have a question. So you mentioned that you consider the threshold to generate these adversarial examples, and for the paper I read that you actually used the threshold to kind of bound the loss function. So once the adversarial reach this threshold, you stop trying to make it, let's say, to reduce even further its probability. I wanted to know what is the insight about that, because that's a bit similar to, let's say, friendly adversarial examples. Like when we reach the boundary, we stop. So what was the goal of this particular setting compared to just continue decreasing the probability of the model until 0, for example?
I think for example, if we assume the attacker is online, so attacker can select the either boundary and hop skip jump attack, because in the fraud detection task, it is rare to output the confidentiality. On the other hand, if we assume that we are developing side, we can test our model, so we can apply zeroth order or other application. Sorry, what is your question?
Well, my question is that in the loss, you seem to bound the loss to a minimal where the threshold is met by this maximum, right?
Yes.
My question was why we don't continue further, I would say. Is it to favorize the other loss, for example, of the distance, or is it to avoid further perturbation?
Your question is about the such norm, how to optimize
about the way you optimize the loss function, the way you define the loss function.
We can use the original loss functions. Sorry, I forgot it, but they are, adversarial robustness toolbox is a very useful tool, and it registers in GitHub, and such the adversarial ART is the provide latest attack algorithm, and we use such repository. But some case, for example, the zeroth order optimization is the ART implement the original the algorithm, but we find that such optimization, the loss function could be modified. So, for example, they stop the original algorithm, original loss function, stop their optimization until reach the attack success. So we continue to it. Sorry. Thank you.
Okay. Thank you.
I actually had a question from Funabiki-san. I already thank you again for the talk. I was wondering, because how realistic is the threat model, the attack that you designed? Because I think, did you consider the number of queries that are being used? Can you use some kind of queries blocker or limitations to protect the system in this case?
Yes, I think that we can consider several mitigation, because for now, so at first we can apply the classical security to the model. For example, you are correct. So if the cloud server detect a lot of queries and very similar queries, they can detect the attack. And so the limitation of the output is also similar mitigation. And in the, of course, we consider the several options. So it contains the machine learning pipeline or other classical security. And I think for now, the real attack is very difficult to use case. But in the future, so some classical security could be broken or other if the attacker can get some skill to evade such existing defensive approach. We should prepare such situation. So in that case, so we can create adversarial examples in the tabular data, so we can execute adversarial training, so using such adversarial examples, and it leads the improve robustness of the model. So that's our idea.
I see. Thank you.
Thank you.
Do we have any other question in the audience? So maybe I have one more. Did you attempt any kind of defense mechanism against these adversarials, like adversarial training, or even when I was going through the paper, I was thinking to masking some features, like or not using some features that are the less robust. Have you attempted any of the classic defense?
Yes, I think so how to say, the filtering, for example, the before the inputting is useful mitigations, and some I think the differential privacy or other masking technique could be applied to these other mitigations.
Mm-hmm. Yes, because that makes me so when I read the paper about this, the importance of features, it reminds me this paper. Other examples are not bugs; they are features, where they're actually trying to remove the features that are the most sensible. And I think this attack is particularly interesting to do that, because you take into consideration the feature importance directly in the attack.
I think so. But I assume that the problem is in the image. Such scenario is very clearly. So I think we can how to say, the several filter to apply the images and consider the adversarial perturbation can be exist or not. On the other hand, in the tabular domain, perhaps there are some critical column. So I mean for example, in our experiments, the purpose or credited history is very important value or important data. So if we mask the tabular data orbitally, so perhaps the masking could be very big affect the output of the model, and this
performance
be ignored.
Okay, thank you. Any other questions?
Maybe to close the meeting, I would like to ask you, Yuki, how you see the future of adversarial attack for industrial systems. What do you think are the main trends or the next challenges that we need to solve as researchers? If you can share some insight with the community.
I think the adversarial examples very, how to say, have been already researched. So I think some target could be covered all machine learning task. So I think maybe it's my personal opinion, but it's difficult to find a new topic in the adversarial examples. On the other hand, the in the adversarial machine learning field, the poisoning attack or other attack is very hot topic. And I think some other attack could be affect the adversarial examples. For example, if the model shift attack, the model inversion attack could be achieved in real use case. The adversarial example is more real threat. So I think that for now, for current situation, adversarial examples is a very big threat, but it's a little bit not real use case. So because the attack capability is very very needed. So on the other hand, if the attack, the model inversion or data poisoning or backdoor attack could be improved, and the limitation of the attack capability of adversarial examples, after that, the adversarial examples is very big issue for machine learning algorithm. That's my opinion.
I see. So thank you very much for your talk, and thank you everyone for joining today.